Before we go any further, two things need to be said plainly because getting them wrong would mean telling you something false. 3i Atlas never sent a signal toward Earth, and it isn't approaching anything anymore. As of right now, it's already past Jupiter. It's roughly 1 billion kilometers out, fading fast, and it is leaving our solar system for good on a path it will never retrace. So if you came here expecting a spacecraft flashing Morse code at our planet, that's not the story. What actually happened is stranger, better documented, and honestly more interesting, because it involves a real scientific controversy, a genuinely rhythmic brightness pattern that earned the nickname Heartbeat, and NASA's own Juno spacecraft nearly getting redirected to chase this object down at Jupiter before it slipped away for good. Everybody, this is the real, complete, current story of 3i Atlas, humanity's third confirmed visitor from beyond our solar system. Why one part of its behavior earned a nickname dramatic enough to spawn 100 conspiracy theories, and exactly where this object actually is right now as it disappears back into interstellar space. We're going to walk through this chronologically, from discovery to departure, because the full arc genuinely matters here, and skipping ahead to just the controversial part is exactly how a real, fascinating scientific story gets flattened into something false. Let's start at the beginning, because the full arc of this story matters. On July 1st, 2025, the Atlas Survey, a network of telescopes based in Chile, built specifically to catch fast-moving, unusual objects before they get away, detected something entering our solar system on a trajectory that immediately stood out from anything native to our own cosmic neighborhood. Its orbit was hyperbolic, with an eccentricity of roughly 6.1, an extraordinarily elongated shape that leaves zero ambiguity about what it means. This object was never bound to our sun's gravity. It arrived from somewhere else entirely, passed through, and was always going to leave again, permanently, following a path that curves once around the sun, and then heads back out into the emptiness between the stars, never to return. That made it only the third confirmed interstellar object in the history of astronomy, following 1i Oumuamua in 2017 and 2i Borisov in 2019. Each of those two prior objects taught astronomers something genuinely important that shaped exactly how the scientific community approached 3i Atlas from the Asor moment it was discovered. Oumuamua, spotted in October 2017, was the very first confirmed interstellar visitor, and it moved so quickly through our solar system that by the time astronomers realized what they were looking at, they only had a matter of weeks to study it before it became too faint to track in any further detail. It displayed a strange, unexplained, elongated shape based on how its brightness varied as it tumbled, and a small but real non-gravitational acceleration that was never fully, conclusively explained, fueling exactly the kind of speculation that would later resurface around 3i Atlas. Borisov, discovered in 2019, behaved considerably more like a typical solar system comet, with a visible tail and coma that made its natural cometary nature far less contested from the start. 3i Atlas arrived into a scientific community that had already lived through one genuinely unresolved interstellar mystery with Oumuamua, which meant researchers were, from day one, both more prepared to study this new visitor rigorously and, in some corners, more primed to look for anomalies that might connect back to that earlier, still unsettled case. When it was first spotted, 3i Atlas sat about 670 million kilometers from the Sun, still within the orbit of Jupiter, moving at a genuinely staggering speed, in excess of 130,000 miles per hour, fast enough on its own to confirm it couldn't have originated anywhere inside our own solar system. Its path also carried a second oddity. Astronomers noticed almost immediately a retrograde, steeply tilted trajectory angled more than 175 degrees relative to the flat plane most planets and comets in our solar system roughly share. NASA's own science communications about the object explained where it likely came from in the simplest possible terms, describing an object that formed around another star entirely, got ejected from that system by some ancient gravitational event, and then drifted alone through interstellar space for what was likely millions or even billions of years, before, finally, by pure chance, crossing paths with our own sun. It approached from the general direction of the constellation Sagittarius, which not coincidentally happens to be roughly where the center of our own Milky Way galaxy sits, suggesting this particular wanderer had been drifting through the galaxy's crowded central regions for a very long time before it ever got anywhere near us. The comet made its closest approach to the Sun, called perihelion, on October 29, 2025, and its journey through the inner solar system included some genuinely close passes by our planetary neighbors. It came within about 29 million kilometers of Mars, close enough that spacecraft already stationed there, including China's Tianwen-1 orbiter, managed to capture direct images of it as it went by. Then, continuing outward, it approached Jupiter, reaching its closest point to the giant planet called Perigove, on March 16, 2026, at a distance of roughly 53.6 million kilometers. And that's where our current story actually starts, because in the months leading up to that Jupiter flyby, this object's behavior produced the single detail responsible for almost everything you've probably heard about it since. If you want the real, accurately reported version of a story like this, not a fabricated signal, but a genuinely fascinating, still debated piece of real astrophysics, subscribe. Now, because understanding exactly what the heartbeat actually is requires understanding how astronomers even study an object like this in the first place. Here's the actual detail behind the nickname, and it's worth being precise about it, because precision is exactly what got lost somewhere between the peer-reviewed data and the version of this story that ends up in a video title. As astronomers tracked 3I Atlas across the second half of 2025, multiple independent research teams using completely different telescopes on different continents measured a repeating rhythmic variation in the object's overall brightness. A team, using the Gran Telescopio Canarias and the 2-meter twin telescope, calculated a rotational period of roughly 16.79 hours. A separate team, working independently with the Southern African Large Telescope and the Nordic Optical Telescope, calculated a closely matching period of 1616 hours, with a measured brightness swing of about 0.3 magnitudes across each cycle. Two entirely separate research groups, using entirely separate instruments, arrived at essentially the same number, a strong sign the measurement itself is genuinely solid. It's worth understanding exactly what this kind of measurement, called a light curve, actually involves, because it's one of the most fundamental routine tools in all of observational astronomy, not some exotic technique invented specifically for this object. Astronomers point a telescope at a target repeatedly over an extended period, carefully recording exactly how bright it appears at each measurement, then plot those brightness values against time. If an object is a perfect, uniform sphere, reflecting sunlight identically from every angle, its brightness, as seen from Earth, would stay essentially constant, no matter how it rotates. Almost nothing in space is a perfect sphere, though, especially comets and asteroids, which tend to be irregular, lumpy, elongated objects, often pockmarked with surface features that reflect light differently depending on which side happens to be facing the Sun and Earth at any given moment. As an irregular object like this rotates, it presents a changing silhouette and a changing mix of bright and dark surface features toward any observer, producing a periodic, repeating rise and fall in measured brightness, with the length of that repeating cycle directly revealing the object's actual rotation period. Astronomers have used this exact technique to measure spin rates for many thousands of solar system asteroids and comets over the past several decades, and light curves showing regular, repeating brightness variation, exactly like the one measured for 3I Atlas, are the expected normal result, not an anomaly. What that measurement actually represents is straightforward, and it's exactly what you'd expect from any tumbling, irregularly shaped object in space, whether it's a comet, an asteroid, or a chunk of space debris. As Atlas rotates, different faces of its nucleus, an object that isn't a perfect sphere, catch and reflect sunlight differently, some angles presenting more surface area or more reflective material toward Earth than others. That produces a periodic rise and fall in observed brightness as the object spins, repeating once every full rotation, roughly every 16 to 17 hours in this specific case. This is not a novel or mysterious phenomenon in astronomy. Rotational light curves like this have been measured for thousands of asteroids and comets throughout our own solar system for decades, and they're one of the most basic, routine tools astronomers use to estimate an object's shape and spin rate. Avi Loeb, the Harvard astrophysicist, who has spent much of the past year publicly arguing that a cluster of 3I Atlas's specific behaviors might warrant considering an artificial origin, was the one who gave this specific rotational brightness pattern its now famous nickname, calling it a heartbeat in a blog post and suggesting the regularity could, in principle, represent something other than simple rotation, potentially periodic engine thrusts, adjusting the object's trajectory, or some kind of internal operational cycle. Loeb has been consistently careful to frame this as a hypothesis worth investigating rather than a certainty, publicly hedging his own confidence in an artificial explanation at somewhere around 30 to 40%. But the framing itself, heartbeat, is evocative enough that it traveled through social media stripped of that careful hedging almost immediately. And by the time it reached wider audiences, phrases like flashing signals and the object is pulsing like it's alive had become common. A meaningful distance removed from the actual, considerably more mundane underlying measurement, a comet slowly tumbling end over end as it reflects sunlight differently from different angles. The mainstream scientific response to that specific framing has been consistent and, frankly, fairly blunt. Jason Wright, an astrophysicist at Penn State University who has spent much of his own career specifically researching technosignatures, meaning he's not a scientist dismissive of the broader search for alien technology on principle, published a detailed rebuttal addressing this, and Loeb's others cited anomalies directly, arguing they fit comfortably within the range of behavior astronomers already expect from natural comets, famously comparing comets to cats in that no two of them behave identically, and that period variation of exactly this kind shows up constantly throughout the solar system comet population without anyone treating it as evidence of anything beyond ordinary rotation. NASA's own public position on 3I Atlas has remained that it is a natural interstellar comet based on its confirmed coma, its visible tail, and the specific mixture of water, carbon dioxide, and carbon monoxide detected venting from it, chemistry fully consistent with how comets are understood to behave, adjusted for the different formation environment of a different star system. There's a second detail from the same period that got wrapped into the broader something strange is happening narrative, and it deserves the same careful, honest treatment. Processing dozens of Hubble Space Telescope images captured between November 2025 and February 2026, researchers identified what appeared to be 3 narrow jets of material extending from the comet's nucleus, spaced with a striking, near-perfect symmetry, roughly 120 degrees apart from one another. Loeb pointed to that symmetry as another item on his list of anomalies, arguing nature doesn't typically produce configurations quite this geometrically tidy. Other researchers in the field pushed back on that characterization directly, noting that curved, arc-like jet structures with regular spacing have actually been documented before in several well-studied solar system comets, including the famous Hale-Bopp and comet Mach-Holtz, a natural consequence of how a rotating, irregularly shaped nucleus vents gas from specific active regions on its surface as those regions rotate in and out of sunlight, producing exactly this kind of periodic, symmetric-looking jet pattern without requiring any engineered explanation at all. It's worth understanding the underlying physics of cometary jets a little more, because the mechanism itself explains why symmetric spacing isn't actually as surprising as it might sound. Comet nuclei aren't uniformly active across their entire surface. Instead, specific regions, often areas where the surface ice is more exposed or less insulated by dust, become active, outgassing sites, venting gas and dust into space as sunlight warms them. As the nucleus rotates, each of these active regions periodically faces the sun, vents material outward, and then rotates back into shadow, repeating that cycle once per full rotation. If a nucleus happens to have a small number of distinct active regions distributed at roughly regular intervals around its surface, a genuinely common outcome given how these regions tend to form around structural features like cracks, ridges, or compositional boundaries in the ice, the resulting jets can appear from Earth's vantage point as a roughly symmetric, evenly spaced pattern, purely as a geometric consequence of the nucleus's rotation and the distribution of its active regions, not because anything about the pattern was deliberately engineered. If a genuinely fascinating, real piece of space science, one involving a real scientific disagreement playing out in actual published research rather than manufactured drama, is exactly what you come here for, subscribe now, because the story of what almost happened at Jupiter is where this gets genuinely exciting, and it has nothing to do with signals. Because here's the part of this story that deserved to go viral and largely didn't: a genuinely bold, real, technically serious proposal to physically chase 3I Atlas down using a spacecraft NASA already had in the right neighborhood. As 3I Atlas approached its closest point to Jupiter in March 2026, Loeb, working alongside researchers Adam Hibbard and Adam Krall from the Initiative for Interstellar Studies, published a detailed orbital mechanics study proposing something genuinely audacious. NASA's Juno spacecraft, which had been orbiting Jupiter since 2016, studying the giant planet's atmosphere, magnetic field, and interior. Structure still had a meaningful amount of propellant remaining, and the researchers calculated that, with a specific, carefully timed thrust maneuver, applied as early as September 2025, followed by what's called a Jupiter-Oberth maneuver, using the planet's own gravity to gain additional velocity efficiently, Juno could potentially be redirected out of its established Jupiter orbit entirely and sent on an intercept course with 3I Atlas during the comet's own closest approach to the planet in March 2026. Firing an engine at that specific point in an orbit produces a dramatically larger change in overall trajectory and velocity than firing the same engine burn anywhere else along the path, essentially letting a spacecraft borrow extra efficiency from the planet's own gravity well. Using Jupiter itself, the largest planet in our solar system, with by far the strongest gravitational field of any planet, as the pivot point for this maneuver, is exactly the kind of technique that could plausibly stretch a genuinely small amount of remaining fuel into a meaningful trajectory change, which is precisely why the proposal's fuel numbers looked as favorable as they did. The numbers behind that proposal were genuinely striking. The team's calculations showed Juno could potentially come within about 27 million kilometers of 3I Atlas using just 110 kilograms of remaining propellant, a mere 5.4% of the spacecraft's original fuel reserve. And Juno wasn't some empty, aging hulk with nothing left to offer. The spacecraft still carried a genuinely capable suite of scientific instruments, including a near-infrared spectrometer, a magnetometer, a microwave radiometer, an energetic particle detector, a radio and plasma wave sensor, an ultraviolet spectrograph, and a visible light camera, any combination of which could have provided humanity's closest, most detailed direct look at an interstellar object we've ever managed to obtain, using hardware that was already built, already launched, and already sitting right there in the neighborhood. Consider what a proposal like this actually represents in the broader context of spaceflight economics. Building and launching a brand new spacecraft specifically to study an interstellar object would take years of planning and design, an enormous budget, and critically, more time than any of these fast-moving visitors typically spend anywhere near our solar system before disappearing. Again, Oumuamua, the first confirmed interstellar object, was gone, too faint to track within a matter of weeks of its discovery, with no existing spacecraft anywhere positioned to reach it in time. The idea of repurposing an already operational mission like Juno, one that happened, by sheer good fortune, to already be sitting in exactly the right part of the solar system at exactly the right time, represents one of the only realistic strategies currently available for getting genuinely close-up data on an object like this within the narrow window before it vanishes for good. That proposal represents genuinely serious, technically rigorous science, published with real orbital mechanics calculations using specialized trajectory optimization software, not idle speculation. It's also worth being clear about where that story actually landed. As of the most recent available information, there's no public confirmation that NASA executed this specific maneuver or successfully redirected Juno to intercept 3I Atlas. The proposal represents a genuinely compelling demonstration of what was technically possible, using a spacecraft humanity already had in position, more than it represents a confirmed mission that actually happened. Whether Juno's own limited remaining fuel, competing scientific priorities for the aging Jupiter orbiter, or simply the tight timeline involved, prevented the maneuver from actually being carried out, isn't something that's been definitively publicly clarified. What we do know for certain is that 3I Atlas made its closest approach to Jupiter right on schedule on March 16, 2026, and continued onward, exactly as its unbound hyperbolic trajectory always guaranteed it would. So where does that leave this object right now, as of today? 3I Atlas has been retreating steadily since its October 2025 perihelion, passing beyond the orbit of Mars, then beyond Jupiter's orbit as well by early 2026. Because its trajectory is hyperbolic rather than a bound elliptical orbit, this isn't a comet that will ever swing back around for a return visit the way Halley's Comet does every 76 years. The shape of its path is a permanent one-time record. It doesn't change with time. Only the comet's position along that fixed path does. By recent tracking estimates, 3I Atlas now sits roughly 1 billion kilometers from the Sun, about 6.7 times the distance between the Earth and the Sun, appearing as an increasingly faint, fading dot, its brightness dropping steadily as it moves farther from both the Sun and Earth simultaneously. It's already well beyond naked eye visibility, and beyond what typical backyard telescopes can detect now, requiring genuinely large observatory-class instruments just to track at all. Within a matter of months, even those instruments will likely lose it entirely, as it fades permanently below the threshold of what any telescope on Earth can meaningfully observe, continuing outward, alone for the rest of its existence, carrying with it whatever remaining secrets about its true composition and origin scientists haven't yet managed to fully decode. That fading, gradual disappearance is itself worth understanding, because it explains why the scientific window for studying 3I Atlas in detail was always going to be tight, regardless of any single agency's specific response speed. Unlike a planet or a bound comet, permanently available for repeated study across years or decades, an interstellar object like this offers researchers a single, narrow opportunity, typically spanning somewhere between several months and roughly a year before it becomes too distant and too faint for any existing instrument to meaningfully track. Every observation, every spectrum, every image captured during that narrow window represents data that, once the object fades from view, simply cannot be replaced or recollected. That's exactly why the level of coordinated international scientific attention this object received, Hubble, Webb, SphereX, ground observatories across multiple continents, spacecraft at Mars, and a serious proposal to redirect Juno makes complete sense, not as an overreaction to a mysterious signal, but as a genuinely appropriate, urgent response to a real, fleeting scientific opportunity that will not come again with this particular object. That's the honest, complete, currently accurate answer to where this object actually is. A fading point of light already 1 billion kilometers past Jupiter, heading permanently back out into the vast emptiness between star systems. Exactly the way it arrived, exactly the way NASA's own trajectory data predicted from the very beginning. It's worth stepping back and appreciating what this entire episode actually represents, stripped of any exaggerated framing. In the span of about 13 months, from its July 2025 discovery to its now confirmed departure past Jupiter, 3I Atlas, became one of the most thoroughly, rigorously studied objects in the recent history of astronomy. Multiple space telescopes, including Hubble, Webb, and Spherex, all turned their instruments toward it. Ground-based observatories across multiple continents tracked its rotation, its color, and its chemistry. Spacecraft already stationed at Mars captured direct images as it passed by. A serious technically detailed proposal was developed to redirect an active NASA mission specifically to intercept it. And throughout all of that genuine, substantial scientific attention, a single natural phenomenon, an object's brightness rising and falling as it slowly rotates, got dressed up in language dramatic enough to convince a meaningful portion of the internet that an alien spacecraft had been signaling our planet. The real story was never less interesting than the exaggerated one. It was, if anything, more interesting, because it's true. A genuine visitor from another star system, quite possibly older than our own solar system itself, tumbled through our cosmic neighborhood for a matter of months, got photographed by human spacecraft on 2 separate planets, sparked a real, published, technically serious scientific disagreement about how to interpret its behavior, nearly triggered a genuinely audacious redirection of an active NASA mission to chase it down, and then, exactly as the math always said it would, kept going, fading into the dark on a path that will carry it away from our solar system forever. If you want the real, complete, currently accurate version of stories like this, the kind that separates genuine peer-reviewed science from exaggerated framing, while still delivering every bit of the genuine fascination the real story actually earns, subscribe and turn on notifications. Because 3I Atlas is still out there fading right now, and if any new, data comes in before it disappears from view entirely. We'll bring it to you the moment it's confirmed.